In this video, we're going to focus on Graham's law of diffusion. The basic idea behind this law of diffusion is that heavy gases move slowly, light gases move quickly. As the molar mass of a gas increases, the rate of diffusion decreases. Now you might be wondering, what is diffusion? Well, let's draw a picture to illustrate this. So imagine we have this container, but in this container there's going to be a small opening or a hole in the container, if you will. And let's put nitrogen gas inside. The rate at which it takes nitrogen to escape from this container through this hole is known as diffusion. So that's what it is. But now let's focus on this problem. The rate of diffusion of argon gas was measured to be 0.218 moles per second at a certain temperature. So let's write that down. Calculate the rate of diffusion for helium gas. So this is what we're looking for. Now the formula for the rate of diffusion is this equation: R2 over R1 is equal to the square root of M1 over M2. So notice the inverse relationship, how the subscript of 2 is on top on the left, but it's on the bottom on the right. That's important when plugging in your numbers. You need to take that into account. So let's say R2 corresponds to helium and R1 corresponds to argon. Molar mass 1 is going to correspond to the molar mass of argon. Molar mass 2 is going to correspond to helium. So make sure you keep track of that. So this is the equation associated with Graham's law of diffusion. Now let's go ahead and calculate the rate of diffusion for helium gas. So we have the rate for argon gas is 0.218. Now what we need is the molar mass of argon and helium, and we could find it using the periodic table. The molar mass of argon is approximately 40, and the molar mass of helium is approximately 4. 40 divided by 4 is 10, and so what we're going to have here is the square root of 10. Now in order to get the rate of diffusion for helium by itself, we need to multiply both sides by 0.218. So the rate of diffusion, let me say that again, the rate of diffusion for helium is going to be 0.218 times the square root of 10. So you should get 0.689 moles per second. So note that the rate of diffusion of helium is significantly greater than the rate of diffusion for argon. And the reason for that is helium is much lighter. So because helium has it has less mass, it's lighter, its molar mass is less, it can diffuse more quickly than argon can because it moves faster. So we could see the relationship between molar mass and rate of diffusion. Now let's move on to the second problem. An unknown gas has a rate of diffusion that is 4 times faster than oxygen gas. Determine the identity of the gas. So what can we do here? Well, let's begin by writing the formula. So we have R2, which let's use 2 for oxygen, over R1. So R1 is going to be the unknown gas. We'll call it gas X. And that's going to equal the square root of the molar mass of gas X divided by the molar mass of O2. So make sure that these subscripts match. And these subscripts, they should match as well. Now, this unknown gas has a rate of diffusion that is 4 times faster than oxygen. So if we give the rate of diffusion for oxygen gas a value of 1, then the rate of diffusion of this unknown gas is 4 times greater. It has to have a value of 4. If we gave oxygen a value of 2, the rate of diffusion of this gas will be 2 times 4, 8. But let's use 1 and 4. Now, in order to determine the identity of the gas, given that we have a multiple choice problem, we need to calculate its molar mass. We know the molar mass of O2. We could find that in a periodic table. It's 16 times 2, or 32 grams per mole. So our goal in this problem is to calculate the molar mass of the unknown gas, and then we can match it with one of the answer choices below. So let's plug in the numbers. The rate of effusion for O2 is going to be 1. The rate of effusion for the unknown gas is 4. And the molar mass of O2 is 32. So first, let's get rid of the square root symbol. Let's take the square of both sides of the equation. 1 squared is 1, 4 squared is 16. On the right side, the square root is going to disappear. So we're just going to get this. So to solve for the molar mass, we need to multiply both sides by 32. 32 divided by 16 is 2. So that's going to be the molar mass of the unknown gas. It's 2. So now, which answer choice corresponds to this answer? It's not going to be N2. N2 has a molar mass of 28. It's not going to be carbon monoxide. That too has a molar mass of 28. It's 12 plus 16. It's not going to be carbon dioxide. That has a molar mass of 44. And it's not going to be helium, which has a molar mass of 4. The answer is H2. Hydrogen gas has a molar mass of approximately 2. So hydrogen gas is the unknown gas. Now let's move on to our last problem. It takes 3.12 seconds for a sample of krypton to effuse from one compartment into another at a certain temperature. Determine the time it takes for an equivalent sample of neon to do the same job. So in this case, this problem is dealing with time and not rate. So how do we solve this one? Well, we need to understand that time and rate are inversely related. As the molar mass of a gas increases, the rate of effusion decreases, which means the time it takes to effuse is going to be longer. Heavy gases, they move slower, which means they take a longer time to get to their destination. So imagine if you want to drive to a destination that's 300 miles away. If you're driving 30 miles per hour, it's going to take you 10 hours to get there. So let me draw a picture or write down some numbers. So let's say you're at point A and you want to get to point B, and the distance is 300 miles. So let's say if you're going at a slow speed of 30 miles per hour, it's going to take you 10 hours to get there. Now, if you're moving faster, let's say at 60 miles per hour, it's going to take you 5 hours to get there. So you can think of the speed as the rate. As the rate decreases, the time increases. If you're driving slower, it's going to take you a long time to get to your destination. So that's what I want you to understand, the inverse relationship between the rate and the time. But the molar mass and the time, there's a, I won't say a direct relationship, but kind of. When one goes up, the other goes up. Now let's go back to Graham's law of effusion. R1 over R2 is equal to the square root of M2 over M1. So because of this inverse relationship between the molar mass and the rate, the subscripts are inversely related. One is on top, the other is on the bottom. But now, the time and the rate are inversely related. So if R1 is on top, T2 is going to be on top. Since R2 is on the bottom, T1 is on the bottom. But between molar mass and time, they're on the same side because when the molar mass goes up, the time goes up. What we need is this portion of the equation to solve this problem. And so we're going to say T2 is going to be, we want to find the time it takes for neon to effuse. So T2 is going to be the time for neon, and T1 is going to be the time for krypton, time it takes for that gas to effuse. And that's going to equal the square root of the molar mass of neon divided by the molar mass of krypton. So because these subscripts match, these gases must match there as well. So that's the formula that we're going to use in this problem. So let's plug in some numbers. The time it takes for neon to do the job, that's what we're looking for. We know the time it takes for krypton to get it done. It's 3.12 seconds. Now, the molar mass of neon using the periodic table, if you look it up, it's 20.18. And the molar mass of krypton is 83.8. Now, what I'm going to do is I'm going to multiply both sides by 3.12 seconds. .18 divided by 83.8, that's 0.2408. Let's take the square root of that number, which is 0.4907, and then multiply by 3.12. So the time it takes for an equivalent sample of neon to do the same job is 1.531 seconds. So that's the answer. So that's it for this video. Now you know how to solve chemistry problems associated with Graham's law of diffusion. Thanks for watching.